Hello and welcome to Earth Science, Lecture 14, Mountain Building. The term for the process that collectively produce a mountain belt is orogenesis, where oros means mountain and genesis means to come into being. Most major mountain belts display striking visual evidence of great compressional forces that have shortened the crust horizontally while thickening it vertically. These collisional mountains usually result from the collision of one or more small crustal fragments with a continental margin, or from the closure of an ocean basin that results in the collision of two major landmasses. As a consequence, collisional mountains contain large quantities of pre-existing sediments and sedimentary rocks that at one time lay along the margins of continents and were subsequently faulted and contorted into a series of folds. Although folding and thrust faulting are often the most conspicuous signs of orogenesis, varying degrees of metamorphism and igneous activity are always present. The theory of plate tectonics provides a model for orogenesis with excellent explanatory power. It accounts for the origin of virtually all the present mountain belts and most of the ancient ones. According to this model, the tectonic processes that generate Earth's major mountain terrains occur along convergent plate boundaries. We will next revisit the nature of convergent plate boundaries and then examine how the processes of subduction can drive mountain building around the globe. Mountain building has occurred in recent geological past at several locations around the world. Young mountain belts include the American Cordillera, which means spine or backbone, which runs along the western margin of the Americas from the southernmost South America to Alaska and includes both the Rockies and the Andes. The Alpine-Himalayan chain, which extends along the margin of the Mediterranean through Iran and northern India and into Indochina, and the mountainous terrain of the western Pacific, which includes the volcanic island arcs like Japan, the Philippines, and much of Indonesia. Most of these young mountain belts have formed in the past 150 million years or so. Some, including the Himalayas, began their growth as recently as 50 million years ago. In addition to these young mountain belts, there are several chains of Paleozoic age mountains in the Earth. Although these older mountain belts are deeply eroded and topographically less prominent, they exhibit the same structural features found in young mountains. The Appalachians in the eastern United States and the Urals in Russia are classic examples of this group of older, well-worn mountain belts. Where oceanic lithosphere subducts beneath oceanic lithosphere, a volcanic island arc and related tectonic features develop. Subduction of oceanic lithosphere beneath continental lithosphere, on the other hand, results in the formation of a continental volcanic arc and mountainous topography along the margin of the continent. Acting like a conveyor belt, oceanic lithosphere may also bring volcanic island arcs and other crustal fragments to a subduction zone. These crustal elements are generally too buoyant to subduct at any great depth, and they become welded to the overriding plate, which may then be another small crustal fragment or continent. If subduction continues long enough, it can ultimately lead to the closure of an ocean basin and the ensuing collision of two continents. Island arcs result from the steady subduction of oceanic lithosphere under oceanic lithosphere, which may continue for 200 million years more or so. Periodic volcanic activity, the emplacement of igneous plutons at depth, and the accumulation of sediment that is scraped from the subducting plate gradually increase the volume of crustal material capping the end of the continental plate. Some larger volcanic island arcs, such as Japan, owe their size to having been built on fragments of continental crust that have rifted from a larger landmass or to the joining of multiple island arcs over time. The continued growth of a volcanic island arc can generate mountainous topography consisting of nearly parallel belts of igneous and metamorphic rocks. This activity, however, is viewed as just one phase of the development of Earth's major mountain belts. As you will see later, some volcanic arcs are carried by subducting plates to the margins of large continental blocks, where then they are involved in large-scale mountain building episodes. So we're going to go ahead and look through some more different types of mountain building. Andean-type mountain building is characterized by subduction beneath a continent rather than an oceanic lithosphere, as in the Andes Mountains of South America. Subduction along these active continental margins is associated with long-lasting magmatic activity that builds continental volcanic arcs. The result is crustal thickening, with the crust reaching thickness of more than 45 miles. The first stage in the development of Andean-type mountain belts occurs along passive continental margins. The east coast of the United States provides a modern example of a passive continental margin, where sedimentation has produced a thick platform of shallow water sandstone, limestone, and shales. At some point, the forces that drive plate motions change, and the subduction zone will develop along the margin of the continent. This subduction zone may form because the oceanic lithosphere has become so old and dense that it begins to sink down under its own accord. Alternatively, strong compressional forces may help initiate this subduction. In an idealized Andean-type subduction, convergence of the continental block and the subducting oceanic block lead to deformation and metamorphism on the continental margin. Once the oceanic plate descends to about 62 miles, partial melting of the mantle rock above the subducting slab generates the magma that travels upward to form those volcanic arcs. Thick continental crust greatly impedes the ascent of magma. Consequently, a high percentage of the magma that intrudes the crust never reaches the surface. Instead, it crystallizes at depth to form intrusive igneous rocks or plutons, as we've talked about previously. Eventually, uplifting and erosion will expose them to the surface as a batholith. During the development of volcanic arcs, unconsolidated segments that are carried on the subducting plate, as well as fragments of oceanic crust, may be scraped off and plastered against the edge of the overriding plate, like a wedge of soil scraped up by an advancing bulldozer. The resulting chaotic accumulation of deformed and thrust-faulted sediments and scraps of ocean crust is called an accretionary wedge. So you can see that right here in the middle of this image. So basically all this material on top of this oceanic plate is getting scraped off as it gets subducted, and it builds up, forming an accretionary wedge. As an accretionary wedge thickens, it acts as a barrier to the movement of sediment from the volcanic arc to the trench. As a result, sediments begin to collect between the accretionary wedge and the volcanic arc. This region, which is composed of relatively undeformed layers, is called a forarc basin. Beginning about 30 million years ago, subduction gradually ceased along much of the margin of North America, and as the spreading center that produced the trench in California. The uplifting and erosion that followed removed most of the evidence of past volcanic activity and exposed the core of crystalline igneous and associated metamorphic rocks that make up the Sierra Nevada. The coast ranges were uplifted only recently, as evidenced by the young, unconsolidated sediments that currently blanket portions of these highlands. California's Great Valley is a remnant of the forarc basin that formed between the Sierra Nevada and the accretionary wedge and trench that lay offshore. Throughout much of its history, portions of the Great Valley lay below sea level. This sediment-laden basin contains thick marine deposits and debris eroded from the adjacent continental volcanic arc. Most major mountain belts are generated when one or more buoyant crustal fragment collides with a continental margin as a result of subduction. Whereas oceanic lithosphere, which is relatively dense, readily subducts. Continental lithosphere contains significant amounts of low-density crustal rocks and is therefore too buoyant for it to be subducted deeply or even permanently. Consequently, the arrival of a crustal fragment at a trench results in a collision between the two continental blocks. A Cordilleran-type orogeny, named after the North American Cordillera, is associated with a Pacific-like ocean, in that, unlike the Atlantic, the Pacific Ocean may never close. The rapid rate of the seafloor spreading in the Pacific Basin is balanced by the high rate of subduction. In this setting, island arcs and small crustal fragments are often carried along until they collide with an active continental margin and accrete or join it onto its edge. This process of collision and accretion has generated many of the mountainous regions that rim the Pacific. These accreted blocks of crust are called terranes. Geologists use this term to describe any crustal fragment that consists of a distinct and recognizable series of rock formations and has been transported and accreted by plate tectonic processes. Notice that terrain is a different word from terrain, as in T-E-R-R-A-I-N. The two are pronounced the same, but terrain, T-E-R-R-A-I-N, refers to the shape of a surface's topography or the lay of the land. What is the nature of the crustal fragments that have been made into these terranes? Well, some may have been microcontinents, similar to the modern-day island of Madagascar, located off the east coast of Africa in the Indian Ocean. Many others were island arcs similar to Japan, the Philippines, and the Aleutian Islands. Still, others may have been submerged oceanic plateaus created by massive submarine outpourings of basaltic lava. More than 100 of these relatively small crustal fragments exist in the modern world. Small structures, such as seamounts, are generally subducted along with the descending oceanic slab. However, thick sections of oceanic crust are dominated by low-density andesitic igneous rocks. They're too buoyant to subduct. In these situations, a collision between the crustal fragment and the continental margin occurs. The upper crustal layer are basically peeled off from the descending plate and thrust in a relatively thin sheet onto the adjacent continental block. Convergence does not generally end with the accretion of a crustal fragment. Rather, new subduction zones typically form seaward of the accreted terrain, and they carry other island arcs or microcontinents toward a collision with the continental margin. Each collision displaces earlier accreted terrains further inland, adding to the zone of deformation as well as to the thickness of the lateral extent of the continental margin. So basically, you just continuously have these microcontinents slamming into your continental plate. They stack up on one another, make more and more deformation occur, and you can get even like a sort of multiple subduction zone occurring in this region. The correlation between mountain building and the accretion of crustal fragments was first developed in studies of the North American Cordillera. Researchers determined that some of the rocks in the orogenic belts of Alaska and British Columbia contain fossils and paleomagnetic evidence indicating that these strata previously lay much closer to the equator. It is now known that many of the terrains that make up the North American Cordillera were scattered throughout the Pacific, like the island arcs and oceanic plateaus currently distributed in the western Pacific. During the breakup of Pangaea, the eastern portion of the Pacific began to subduct under the western margin of North America. This activity resulted in many additions of crustal fragments along the entire Pacific margin of the continent, from Mexico's Baja Peninsula to northern Alaska. Geologists expect that many modern microcontinents will likewise be accreted to active continental margins around the Pacific, producing new orogenic belts. ALPINE-type orogenies are episodes of mountain building that occur when two continental masses collide. So we've talked about island arcs, which is when two oceanic plates collide. We've talked about our Cordilleras and our Andean mountain types. So now we can look at alpine, when we have two land masses colliding. They are named after the Alps, which have been intensively studied for more than 200 years. Mountain belts formed by the closure of major ocean basins includes the Himalayas, the Appalachians, the the Urals, and the Alps. Continental collisions result in the development of mountains characterized by laterally shortened and vertically thickened crust, achieved through deformation such as folding and large-scale thrust faulting. Prior to the collision of the two large landmasses, this type of orogeny may also involve the accretion of smaller continental fragments or island arcs that occupied the ocean basin that once separated the two continental blocks. The zone where two continents collide and are welded together is called a suture. The same term can be used to describe the boundary between two adjacent accreted terrains, like we talked about just a moment ago. So next, we will take a closer look at two examples of collisional mountains, the Himalayas and the Appalachians. The Himalayas, which is Earth's youngest collisional mountains, are still rising. By contrast, the Appalachians are much older, and most of the building has ceased about 250 million years ago. So let's take a look at each. The mountain building episode that created the Himalayas began between 50 and 30 million years ago, when India began to collide with Asia. Prior to the breakup of Pangaea, India was located between Africa and Antarctica in the southern hemisphere. As Pangaea fragmented, India moved rapidly, geologically speaking of course, a few thousand kilometers in a northward direction. The subduction zone that facilitated India's northward migration was near the southern margin of Asia. Continued subduction along Asia's margin created an Andean-type plate margin that contained a well-developed continental volcanic arc and an accretionary wedge. India's northernmost margin, on the other hand, was a passive continental margin consisting of a thick platform of shallow water sediments and sedimentary rocks. Geologists have determined that two or perhaps more small crustal fragments were positioned on the subducting plate somewhere between India and Asia. During the closing of the intervening ocean basin, a small crustal fragment, which now forms southern Tibet, reached the trench and was accreted to Asia. This event was followed by the docking of India itself. As the intervening ocean basin was closing up, the more deformable materials on the continental margins of these landmasses became highly folded and faulted. Two major thrust faults and many smaller ones sliced through the Indian crust. Subsequent motions along these thrust faults caused slices of the Indian crust to be stacked up on one another. Today, these slices make up the bulk of the highest peaks in the Himalayas, many of which are capped by tropical marine limestone and formed along what was once a continental shelf. The formation of the Himalayas was followed by a period of uplift that raised the Tibetan Plateau. Seismic evidence suggests that a portion of the Indian subcontinent was thrust beneath Tibet, a distance of perhaps 250 miles. If this occurred, the added crustal thickness would account for the lofty landscape of southern Tibet, which has an average elevation of more than 14,800 feet, higher than the tallest mountain in the contiguous United States. The collision with Asia slowed but did not stop the northward movement of India, which has since penetrated at least 1,200 miles into the mainland of Asia. Crustal shortening and thickening accommodated some of this motion. Much of the remaining penetration into Asia caused lateral displacement of large blocks of the Asian crust by a mechanism described as escape tectonics. When India continued its northward trek, parts of Asia were squeezed eastward out of the collision zone. These displaced crustal blocks include much of Southeast Asia and sections of China. So that's one of the newer mountain ranges, but let's talk about one of the older ones. The Appalachian Mountains provide great scenic beauty near the eastern margin of North America, from Alabama to Newfoundland. Mountain belts of similar origin that formed during the same period and were once contiguous and found in the British Isles, Scandinavia, Northwest Africa, and Greenland. The orogenies that generated this extensive mountain system lasted a few hundred million years and resulted in the assembly of the supercontinent of Pangaea. Detailed studies of the Appalachians indicate that this mountain belt was the result of 3 distinct episodes of mountain building. Our simplified overview begins 750 million years ago with the breakup of a supercontinent called Rodinia that predates Pangaea. Much like the breakup of Pangaea, this episode of continental rifting and seafloor spreading generated a new ocean between the rifted continental blocks. Located within this widening ocean basin was a microcontinent near the edge of ancestral Africa. About 600 million years ago, for reasons geologists do not completely understand, plate motion changed dramatically and this ocean basin began to close. This led to the development of multiple subduction zones, and the stage was set for the 3 orogenic events that would lead to the collision of North America and Africa. So let's take a look at this in steps. Around 450 million years ago, the marginal sea between the volcanic island arc and ancestral North America began to close. The collision that ensued, called the Taconian orogeny, caused the volcanic arc along the ocean with sediments located on the upper plate to be accreted to the edge of the larger continental block. The remnants of this volcanic arc are ocean sediments and recognized today as the metamorphic rocks through much of the Appalachian mountain belt. For example, schists beneath New York City and Washington, D.C. formed at the same time. In addition to this pervasive regional metamorphism, numerous magma bodies intruded the crustal rocks along the entire continental margin. A second episode of mountain building, called the Arcadian orogeny, occurred about 350 million years ago. The continued closing of this ancient ocean basin resulted in the collision of a microcontinent with North America. This orogeny involved thrust faulting, metamorphism, and the intrusion of many large granitic bodies. This event also added substantially to the width of North America, particularly in eastern New England. The final orogeny, called the Alleghenian orogeny, occurred about 250 and 300 million years ago, when Africa collided with North America. This collision displaced material that was accreted earlier by as much as 155 miles toward the interior of North America. This event also displaced and further deformed the continental shelf sediments and sedimentary rocks that had once flanked the eastern margin of North America. Today, these folded and thrust-faulted sandstones, limestones, and shales make up the largely unmetamorphosed rocks of the Valley and Ridge province. This structural signature of mountain building can be found as far inland as central Pennsylvania and West Virginia. With the collision of Africa and North America, the young Appalachians, perhaps as majestically as the Himalayas, lay along the suture in the interior of Pangaea. The tectonic forces that built the mountains ceased to drive them upward. Then, about 180 million years ago, the new supercontinent began to break into smaller fragments, a process that ultimately created the modern Atlantic Ocean. Because this new zone of rifting occurred east of the suture that formed when Africa and North America collided, remnants of Africa remain stuck to the North American plate. Okay, let's go ahead and give a few questions a shot. This is the last lecture on Earth's solid portion. From here, we're actually going to shift to atmospheres. So let's go ahead and wrap this up with a few questions. Number 1, blank is the term for the processes that collectively produce a mountain belt. Okay, well, we use this term a lot. It's orogenesis. An episode of mountain building is called an orogeny. Number 2, Japan is an example of blank. Well, Japan is easy for me to think about in this case because it's in the middle of an ocean. So to me, that means probably 2 ocean plates meeting, which means it's an island arc type mountain building episode. And last question, number 3, Subduction of oceanic lithosphere beneath a continent to produce continental volcanic arcs occurs during what type of mountain building? So we have discussed quite a few, and this is a good recap. Forces you to look back through the notes or the video, and you'll see that the answer is A. Andean-type mountain building is characterized by subduction beneath a continent rather than oceanic lithosphere. Okay, well, as always, thanks for watching, and have a great day.